OCR A-Level Chemistry A, Periodic Table, Elements and Physical Chemistry, June 2018. Question 1. A sample of boron contains the isotopes B10 and B11. The relative atomic mass of the boron sample is 10.8. What is the percentage of B11 atoms in the sample of boron? So if we have the two borons, one is 11 and one is 10, and the relative atomic mass is 10.8, which means 10.8 is right here. So we got higher percentage of 11 than the 10. So we can say that the percentage of 11 will be 80% because it's closer by 20, and the percentage of the 10 will be 20%. So we can then say 10 times 20% over 100 plus 11 times 80% over 100. So that would be 2 plus 8.8, and that equals 10.8 is 80%. So that's C. Question number 2. In the compound iodine chloride plus and antimony chloride 6 minus, the oxidation number of chlorine is -1. What is the oxidation numbers of iodine and antimony in the compound? So for the first compound, the iodine and Cl2 overall charge is +1. The +1 -1 times 2 is -2, and for iodine, therefore iodine will become +1 +2, adding 2 to both sides, and therefore it will be +3. Iodine is +3 in this case. In the case of antimony, where we have the Sb, that's antimony, Cl6, overall charge is -1. We can say -1, and chlorine is -1 times 6 is -6, and Sb, therefore Sb will be equal to -1 plus 6, adding 6 to both sides, and therefore it's +5. We're looking for +3 and +5, and that would be C. Question 3. What is the number of hydrogen atoms in 0.125 mole of C2H5OH? That's ethanol. 1 mole of ethanol. How many hydrogen atoms are there? In 1 mole, we have 6.023 times 10 to power 23 compound. But we don't have 1 mole, we've got 0.125 mole. So to times that by 0.125 mole, it would be 0.125 mole will then be equal to, if you times that to by 0.125 mole, that would be 6.023 times 10 to power 23 times 0.125 mole. But there are 6 hydrogens in this compound. There are 6 hydrogens. You can see 5 and 1 times that by 6 for the number of hydrogen atoms in there. The answer I'm looking for will be 6.023 times 10 to power 23 times 0.125 times 6, and that should be equal to 4.51. Well, 5 times 10 to power 23 if you use 6.022, and that's what you get for the amount of hydrogen atoms in there, and the answer will be B. So you have to put B here. Question 4. A student titrates a standard solution of barium hydroxide with nitric acid, 25 centimeter cube of 0.045 mole per decimeter cube of barium hydroxide are needed to neutralize 23.35 centimeter cube of nitric acid. What is the concentration in mole per decimeter cube of the nitric acid? First is to balance the equation here. We got the nitric acid plus barium hydroxide, and that gives barium nitrate. Nitrate is 2 power -1. 2 nitrates to balance barium, because barium is in group 2, will be +2, so you have to have 2 there, plus H2O, the water, hence neutralization reaction. And since we got two nitrates here, 2 times nitrate, so you have to multiply this by 2 to balance the nitrate. Put 2 there, and now we have 2 hydrogens and 2 hydrogens, so you only got 2 here again, so you have to multiply this by 2 to balance the hydrogen. And therefore, we now balance the equation. The stoichiometric mole in this equation are 2, 1, 1, 2. What we can say now is to write down the stoichiometric mole. Na is 2. The concentration of acid is we're looking for. The volume of acid, we've got that, is going to be the acid volume here divided by 1000. We would get 0.02335 decimeter cube. And also for the base, we have the Va. Na is 2. For the base, Mb is 1. And Cb is concentration of base at 0.045 mole per decimeter cube, and the volume of base will be 0.025 decimeter cube. We can use straightforward formula Ca Va over Na equals Cb Vb over Nb. We know we're looking for Ca, and that implies that Ca equals, let's put it here, Ca equals Cb Vb Na over Va and B. Ca will be equal to, so we got Cb, which is 0.045 times Vb, 0.025 times Na. Na is 2 divided by the Va, so Va is 0.02335 times Nb, which is 1. Therefore, Ca will be equal to 0.0964. And that's what we're looking for here. That's D. Remember that we have used mole to be equal to concentration times volume. Mole is concentration times volume of acid, and the concentration of times volume of base, but the ratio of the stoichiometric mole is also put in there, and that's how we get our formula. And this one is now saying Ca, which is what that is. All I did was rearrange that one, multiply that by that, so that goes there, and divide it by Va to just make Ca the subject. Question 5. Which statement best explains why nitrogen has a larger first ionization energy than oxygen? So A, nitrogen atoms have less repulsion between p orbital electrons than oxygen atom. Well, in order to answer this question, we need to write down the electron configuration for both atoms. For nitrogen, this is 14,7. That would be 1s2, 2s2, 2px1, 2py1, 2pz1. And for oxygen is 16,8, and that is 1s2, 2s2, 2px. Well, that would be 2 here, and 2py1, 2pz1. We need to A, nitrogen atoms have less repulsion between p orbital electrons than oxygen atoms. Well, you can see the repulsion here is spin up, spin down in the same orbital, higher repulsion here than repulsion between that orbital and that orbital and that orbital. So this is less repulsion. Orbitals are a bit further apart compared to that one, which is same orbital here, and these are different orbitals, so there's more repulsion here. A is correct. Tick A, and we have to put A there. We can confirm that by reading through the rest of them. For B, nitrogen atoms have a smaller nuclear charge than oxygen atom. Well, because you're adding more electron to oxygen and more proton, the nuclear charge of oxygen will be smaller than nitrogen. So this is false. So that's not true. The nitrogen atom loses an electron from the 2s subshell, while oxygen atom loses an electron from the 2p subshell. Oxygen atom loses electron from 2p orbitals, but nitrogen also loses electron from 2p orbitals. This is not true as well, so this is wrong. The final one is D. The nitrogen atom have an odd number of electrons, while oxygen atom have an even number, but that's got nothing to do with the ionization, first ionization energy. And also we know that it increases diagonally. D is not true. The only true answer is A. Question 6. In the periodic table, element X is in group 2 and element Y is in group 15 or 5. What is the likely formula of an ionic compound of X and Y? Okay, so for group 1, the oxidation number is +1, and the group 2 +2, group 3 +3, group 4 +4 or -4, group 5 -3, group 6 -2, group 7 -1, and group 8 0. If you are element of group 2, you will have oxidation number of +2. X is group 2, for X will be 2+. And if you are group 15, that's group 15 here, or 5, that will be 3-. So Y is 3-, which meant that if you take the magnitude of the charge and you take it to the subscript of the opposite element, compound or ionic compound that will be formed will be X3, Y2. So we are looking at C here, and that will be the compound. Question 7. Which statement about ammonium carbonate is not correct? A. It reacts with barium nitrate to form a white precipitate. Ammonium carbonate will be NH4CO3, but the NH4 is +1 and CO3 is 2-. That will be 2 there. Ammonium carbonate. That is reacting with barium nitrate. There will be 2 nitrates there because nitrate is NO3- and barium is 2+. The 2 we go to there and the 1 we go there. That's how we got our formula. Okay, these two reacting will form barium carbonate plus ammonium nitrate. 2 there because we got 2 ammonium and 2 nitrates. See, 2 nitrates and 2 ammoniums. We have 2 here. 2 ammonium and 2 nitrates. 1 barium, 1 carbonate. So that's balanced. This is white precipitate. B, it effervesces with dilute nitric acid. It gives gas with dilute nitric acid. That should be true because if we react NH4CO3, but we put 2 here, plus HNO3, we would get ammonium nitrate, NH4NO3, plus carbonic acid, but we need 2 of those and 2 of those. It's H2CO3 will decompose into H2O plus CO2. We get carbon dioxide gas, and that's the effervescence that we get. That's correct as well. C, it releases an alkaline gas with sodium hydroxide. Yes, if we react ammonium carbonate and NH4, remember it's 2 because NH4 is +1 and carbonate is 2-. You need 2 NH4 to balance with the carbonate and plus sodium hydroxide. You shall be getting ammonium hydroxide and sodium carbonate. So we get sodium carbonate and plus ammonia plus water. And the alkaline gas is ammonia. That will be correct as well. Tick that, that's correct. And finally, ammonium is NH4 plus and CO3 is 2-. The 2 we go there and the 1 we go there. That's why the formula is NH42CO3. D is wrong, so the answer is D, because the question says which statement about ammonium carbonate is not correct. D is not correct. Question 8. A reaction is first order with respect to reactant X. Which rate concentration graph for reactant X is the correct shape? For a first order reaction, we're looking for rate. We know it's going to be directly proportional to the concentration X, and it's of the order of first order. First is 2 power 1, which means rate equals K to the first order concentration of X. Compare that with Y equals mx plus C, but C equal to 0. Compare that to Y equals mx, where we can say that we're looking for a linear relationship going through the origin. We got a rate here and we got the concentration there. It's a linear relationship going through the origin. The answer is going to be A. Write A in the box. Question 9. The reversible reaction of sulfur dioxide and oxygen gas to form sulfur trioxide is shown below. That's sulfur dioxide and oxygen gas forming sulfur trioxide. An equilibrium mixture contains 2.4 mole sulfur dioxide, 1.2 mole oxygen gas, and 0.4 mole of sulfur trioxide. The total pressure is 250 atmospheric pressure. What is the partial pressure of sulfur trioxide? First of all, we need to just write the partial pressure equals mole fraction times total pressure. And just to remind you, this is total pressure, this is mole fraction, and that's partial pressure. And we know what the total pressure is. First of all, we want to find the mole fraction of sulfur trioxide. Lambda of SO3 will be the mole of sulfur trioxide over the total mole, and that will be, we know what the total mole is adding that plus that together, 0.4 over 2.4 plus 1.4 or 1.2 rather, plus 0.4, and that will be 0.4 over 4, and that equals 0.1. But we're looking for partial pressure. The partial pressure for SO3 will be the mole fraction, which is 0.1, times the total pressure, which is 250, will be 25 atmospheric pressure. And what's got 25 atmospheric pressure? That's B. Question 10. A buffer solution is prepared by mixing 200 centimeter cube of 2 molar propanoic acid with 600 of 1 molar sodium propanoate. Ka for propanoic acid is 1.32 times 10 to the power minus 5 molar. What is the pH of the buffer solution? Well, to find the pH, we need to find H plus concentration. And to find the H plus concentration, we can use the Ka. But first of all, mole is concentration times volume. And we know that Ka also has a formula. Ka is, well, concentration of H plus times the concentration of A minus, that's sodium propanoate, is A minus, divided by the concentration of acid, which is propanoic acid. But we need to first of all make H plus the subject, so concentration of H plus, which is what we're looking for, will be the Ka times the concentration of propanoic acid, which is Ha for propanoic acid, divided by the concentration of the sodium propanoate, which is A minus. What we now need to do is find and then write the equations for concentration of the acids and concentration of the propanoate, sodium propanoate. But we know that Ka times the concentration C equals mole over volume. We can do that for the acid here, mole of acid over volume of acid for the first one, which is the same volume as the mole of sodium propanoate, which is A minus, over the volume. Because they're all in the same volume, we can then continue by writing the H plus concentration to be Ka times the mole of acid over volume times volume over mole of A minus. Because this is fraction divided by fraction, and you turn the divide into times, so that's that one becomes times. So you have to flip this, and you can see the volume counts with volume, so you don't even need to calculate the concentration. You can now find the H plus concentration to be Ka times the ratio of mole of acid over the sodium propanoate mole. And for the mole is concentration times volume, we got 1.32 for the Ka value times 10 to the power minus 5, and then times that by the mole of the acid, which is volume of acid, which is 200 times 10 to the power minus 3, so divided by 1000 to convert it to decimeter cube, times 2 volume times concentration for the acid, and that's that. And we need to then divide it by the 600 times 10 to the power minus 3. We got that volume here, which is 600 times the concentration, which is 1 times 1, and that will give the value for H plus concentration, and that gives 8.8 times 10 to the power minus 6 mole per decimeter cube. Find the pH value. pH equals to minus log 10 concentration of acid, and that is minus log of base 10 times 8.8 times 10 to the power minus 6, and so the pH is 5.06, and what has 5.06 here is C, so we have to put C in the box. Question 11. The table below shows the standard entropies for CO, H2 and CH3OH. What is the entropy change for the following reaction? To find the entropy change, which is what we call delta S is equal to delta S of product minus delta S of reactant. And we know the delta S of product, which is, this is the product here, and that's the reactant here. Delta S of the product is 239.7 minus, open bracket, the delta S of reactant, which is for CO, it's 197.6, and for H2, well, there's 2 molar value here for H2. So if we look at the H2 there, we can see for there is 2 molar stoichiometric mole, and that's 1, and that's 1. After times that by 2 times the value for hydrogen, which is 130.6. Hydrogen gas is 130.6, and close bracket. Plugging that into calculator, we get minus 219.1 joules per mole per Kelvin. That will be the change in entropy for delta S. What has the minus 219.1 is A, so we have to put A there. Question 12. The redox equilibria for a hydrogen-oxygen fuel cell in alkaline solution are shown below. The water plus 2 electrons to give you hydrogen gas plus OH minus aqueous. Electrode potential is minus 0.83 volts. I have oxygen gas plus water plus 2 electrons to give 2 OH minus aqueous, and the potential is 0.4 volts. What is the equation for the overall cell reaction? In this situation, we look at the potential. The more positive potential stays, and the less positive is reversed. Going to reverse that one, and this one stays, is to write down the one that stays first. I have O2 plus H2O plus 2 electrons, and that gives 2 OH minus. The one that's reversed is going to be H2 plus 2 OH minus, and that will be 2 H2O plus 2 electrons. One that's reversed is releasing the electron, and this is releasing 2 electrons, and this one is receiving the 2 electrons. The overall reaction will be, well, that 2 electron, we cancel that 2 electron. 1 water, we cancel that water, and the 2 OH minus, we cancel that 2 OH minus. I've got H2 left plus a half O2 gas left, and on this side I've got 1 water, H2O. That will be the overall reaction. Answer which one has that. We can see that H2, because it's asking what is the equation for the overall cell reaction, and this is the equation for the overall cell reaction. So that's that one here. So because it's D, I can then circle D and write D in the box. Question 13. Which enthalpy changes is or are endothermic? 1. The bond enthalpy of CH bond. A CH bond means you have to break the bond. So the bond enthalpy means the energy required to break that bond. If you're breaking that bond, that's endothermic. It's going to be delta H plus. That's bond breaking. Bond breaking is endothermic. Number 2, the second electron affinity of oxygen. Electron affinity is the energy required to add electron to an element. If you have oxygen, you're adding an electron. That's the first electron affinity. That would be O minus. And now to add another electron, O minus plus E minus. So this is now the second electron affinity. Well, that would be a repulsion. That's very difficult. You have to put energy in to add the second electron. That would be O2 minus. And that requires energy. That is endothermic. Delta H here is positive. 1 is correct, 2 is correct. The standard enthalpy change for formation of magnesium. Well, magnesium is basically an element which has already formed. Delta H for that one is going to be 0 because it's already formed. It's not a compound, it's an element. 3 is not correct. It will not be D, it will not be C, it will not be A, it will only be B. So we have to put B there. Question 14. Which statements explains why reaction rates increase as temperature increases? 1. The activation energy is less. Well, the activation energy is always the same for a reaction, but what matters is you want more molecule to have that activation energy or beyond activation energy so they can go on to the product. The activation energy is always the same. Now, that is wrong. Number 2, collisions between molecules are more frequent. If the temperature goes up, kinetic energy goes up, because we know that the basic equation we tend to use for that is the total energy of a system is total kinetic energy plus total potential energy. If the temperature goes up, the kinetic energy goes up. That's correct. Number 3, a greater proportion of molecules have energy greater than the activation energy. That's true. The energy number of molecule profile, that's the number of molecules, and this is the energy at a particular temperature, and another energy at a higher temperature. And we have the activation energy somewhere here. More molecule will acquire energy at a higher temperature. This is true here for number 3. The answer we're looking for are 2 and 3, which is C, and we have to put C in the box. Question 15. Which statement or statements is or are correct for the complex platinum ammonium 2 chlorine 2? 1. One of its stereoisomer is used as an anti-cancer drug. That seems to be correct because the anti-cancer drug, which is cisplatin, and that has a structure of platinum center, and the ammonia and chlorine with another chlorine with a wedge here, and that's Cl, and another ammonia. That looks like square planar. That's NH3. 1 is correct. Number 2, it has a bond angle of 109.5. That bond angle of 109.5 is tetrahedral. That's tetrahedral. And this is not tetrahedral. This is square planar. It has optical isomer. Well, it doesn't have optical isomer. That's wrong as well. We're only looking for D. We have to put D there. Question 16. This question is about enthalpy changes. Part A, Table 16.1 shows enthalpy changes that can be used to determine the enthalpy changes of hydration of fluoride ions, F-. Explain what is meant by the term enthalpy change of hydration. This is a recall question, and to define, we can say the enthalpy change of hydration is the energy required when 1 mole of gaseous ion react or dissolve in water to form 1 mole of aqueous or hydrated ion. This is a recall, and you must mention 1 mole of gaseous ions dissolving in water to form 1 mole of aqueous or hydrated ions. Then you get 2 marks because this is a 2-mark question. Part 2. The enthalpy change of hydration of fluoride ion can be determined using the enthalpy changes in table 16.1 and the incomplete energy cycle below. On the dotted lines, add the species present, including states symbols. So the lattice entropy is when the solid is formed from its gaseous ion. Solid forming, which is calcium F2 solid, and that value for that is -2632, as we've been given 30, as it's been given in the table, and it's forming from its calcium gaseous ion. That'll be calcium 2 plus, and that's gas, plus 2 fluoride ion, again gas, and we have the enthalpy of aqueous now. We're going from calcium 2 plus gaseous to calcium 2 plus aqueous, and that will be hydration of calcium is -1609 and plus 2F minus gaseous. And the next stage is hydration of fluorine, which is what we're looking for. Fluorine, let's just call that X. We're going to get calcium 2 plus aqueous, it's been hydrated, plus 2F minus aqueous. Calcium is in group 2, so you have 2 plus because it's losing 2 electrons, and the fluorine is in group 7, so it's gaining an electron, so it will have -1. This one will be the solution of calcium fluoride, and so we can fill that up, and that will be +13. Part 3. Calculate the enthalpy change of hydration of fluoride ion, F minus. Here I can see that's minus, that's plus, that's minus, and that will be another value here which looks like -2630 plus 13 equals to, so that's on the left hand side here, and that should be equal to, on the right hand side will be -1609 plus, we can just call that X, or we can say it's minus X, but I've chosen plus X and I'm just adding that to that. I don't know what X is, and therefore X will be equal to, just to explain what I've just done, this is -2630, and this one is plus 13, and this one is minus, it's on the right hand side, which is -1609, and that's X. So that's what I've done here. It's the left hand side and the right hand side. Make X the subject, which means I'm going to get -2630 plus 13, then plus 1609. X will be equal to -1008, and because X is 2F minus, and that will be equal to -1008. What would the F be? Will be equal to 1008 divided by 2, which is minus, and that would be equal to -504. Answer we're looking for here would be -504 kilojoules per mole. Part 4. Predict how the enthalpy changes of hydration of fluoride ion and chloride ion will differ. Explain your answer. Well, in this case, for the fluoride, we know fluoride is smaller compared to chloride ion. Chloride ion are bigger. This will be the fluoride ion, and that will be the chloride ion. Delta H of hydration for fluoride ion, that delta H is more, it's going to be more exothermic than delta H of hydration of chloride ion. Why? Because the fluoride ions have smaller radius or size compared to the chloride ion. As we know, we can see that the smaller size ion will linked to a greater attraction to water, because they will be embedded into the water with a greater attraction. Part B, fluorine reacts with steam as shown in the equation below, and the average bond enthalpy as shown in the table. Explain what is meant by the term average bond enthalpy. Well, the average bond enthalpy is the energy required to break 1 mole of a bond in gaseous molecule. Energy required to break 1 mole of bonds in gaseous molecule, where you get the 2 marks for the breaking of bond in gaseous molecule, especially 1 mole. B, part 2. Calculate the bond enthalpy of the FF bond, and we need to give our answer in kilojoules per mole. This is the equation we're using here, and this is the reactant, and that's the product. So this is bond breaking, and that's bond making, and this is the enthalpy of reaction here. We need to find the bond enthalpy here, and to do that, I'm going to do the bond breaking minus the bond making. The sum of bond breaking minus the sum of bond making equals, as has been given here, that equals that, minus 598. You're breaking the reactant first, so that's why it's called bond breaking, because you have to break that bond, and then you rearrange them and make a new bond here and a new bond. So the bond making here is the product one, and the bond breaking is the reactant one. For the reactant, so we've got 2 fluoride bond, 2 fluorine bond, that's 2 there, 2 of those, and water is 2 as well. Altogether it's 4 OH bond, because water is OH, another OH, so that's 2, and then there's 2 of them, so that's 4 OH bond. I could also draw the structure to make it clearer. OH there and H. So, but we need 2 of those. And for fluorine, you can see that's 2F. I'm going to make the oxygen bond, so that's oxygen double bond plus hydrogen fluoride, HF, that's 4 of those. We're trying to find the bond enthalpy for fluorine bonds. Let's call that 2x, because we don't know what bond F is, plus the water is 4 times OH bond, 4 times 4, 6, 4. To take away now a bond breaking, we want to take away from the bond making, and the oxygen bond, which is 498, plus 4 times HF bond, 5, 6, 8. Altogether should be equal to minus 598. 2x plus 1856 minus 498, and minus, open another bracket there, 2272, and that equals minus 598. 2x minus 914 will be equal to minus 598. 2x will be equal to 316. Therefore, x will be 316 over 2, and that equals 158. Bond enthalpy for FF bond is 158 kilojoules per mole. This is going to be a plus, and you have to put a plus there to indicate that it's endothermic rather than exothermic, because if you don't put any plus, it might be assumed that you're not sure whether it's negative or positive. This is definitely positive. Obviously, it's bond breaking, so it should be positive because it's endothermic. Question 17. This question is about reaction rates. Aqueous iron 3 ions, Fe3 plus aqueous, react with aqueous iodide ions, I minus aqueous, as shown below. A student carries out 3 experiments to investigate how different concentration of iron 3 plus aqueous and iodide aqueous affects the initial rate of this reaction. These results are shown below. A. Determine the rate constant and a possible 2 steps mechanism for this reaction that are consistent with these results. So looking at the order of reaction here, when keeping the iodine constant, between that and that, iodine is constant and iron is doubled, that means it's times 2. And if you look at the rate is also double, so it's times 2. And that meant that the rate with iron will be equal to K, the concentration of iron, 3 plus aqueous, to power of 1. Because when we double iron, the rate also doubles, so it's ratio 1 to 1. So therefore, Fe3 plus is first order. Now we need to look for the effect of iodide, keeping the iron constant. So between experiment 1 and 3, iron is constant, but the iodine has doubled, so that's times 2. And what happened to rate between there and there? It has quadrupled 4 times. And when this one is times 2, so that means it is ratio 1 to 2. If we write the rate for iodide, is going to be aqueous to the power of 2. And iodide is second order. The overall order of reaction is 1 plus 2 equals 3. To find the value of K, K will be equal to rate over the iron concentration and iodide to power 2 concentration. And that will be equal to, we pick the first one here, that one here, that will be 8.10 times 10 to the power minus 4 divided by, we have to use the concentration here and there, 4.00 times 10 to the power minus 2 times 3.00 times 10 to the power minus 2 all squared. And that will give 22.5 decimeter to the power 6 per mole squared per second. Note that the unit here is the concentration per second, which is mole per decimeter cube. And the bottom two is also concentration, and is also concentration. So that will be concentration per cube. Working out the unit will concentration cancel another concentration. You're going to get concentration squared, because the cube at the bottom will cancel, because this is 1 and that's 2. So that's concentration cube. When the top one cancels the bottom one of those, so you got concentration squared. You still got the per second, so that's why you got the per second here. Per concentration squared, so that's why the mole becomes per minus 2 mole second, and that will be per decimeter to power 6, because it's per decimeter cube, or it's per decimeter power 6. But inverse of that will make it decimeter to power 6 and per mole squared, and that's how you get the unit here. Finally, we need to work out a 2-step mechanism to this reaction. With the slow step, iron 3 plus aqueous plus 2I minus, because they have to be involved in the rate equation. So that's why we have them there, because they are in the rate equation. That's aqueous as well, to give FeI2 plus, because as you can see, the Fe is 3 plus, the I is 2 minus. If you work out the charge, if this is plus 3 minus, that's minus 1 times 2 is minus 2. The overall charge has to be plus, so that's why this is plus. It has to balance out on both sides of the equation, so that's why this is plus. And if we carry on now, so that's a slow step. And for a fast step, we can then have the same product, Fe2 plus Fe3 plus aqueous, to then go to 2Fe2 plus aqueous plus I2 aqueous. That's the first step. And if we draw a line here for the overall reaction, we will notice that we cancel that one. We write down the final product, we get Fe3 plus Fe3 plus will be 2 Fe3 plus aqueous, plus we have 2I minus aqueous again, going to 2 Fe2 plus, and that's this one here, the iodine solution, iodine liquid. So that's aqueous plus iodine, I2 aqueous. That will be the overall, which is what we were given in the equation for the reaction. That's the 2 Fe3 plus there, plus 2 I minus, going to form 2 Fe2 plus. That's Fe2 plus, by the way, I2. So this is the slow step. Slow step is always involving a rate equation, and this is the fast step. And adding them together, we produce the equation for the reaction. Part B. A student carries out an investigation to find the activation energy EA and the pre-exponential factor A of a reaction. The student determines the rate constant K at different temperatures T. The student then plots a graph of ln K against 1 over T as shown below. Draw a best fit straight line and calculate the activation energy in joules per mole. Give your answer to 3 significant figures. Show your working. Okay, so we've drawn the graph here, and now I need to pick 2 points on the graph. So I'm picking 2 points here, 1 point there and that point there. I need to then find the gradient for this point. Obviously it's a negative gradient, so that distance, the height and that length is point number 1. Point number 2, the gradient m will be equal to change in ln K over change in 1 over T, 31.25 minus 27.3 over, that's 5 minus 0 times 10 to the power minus 3. M is 3.95 over 5 times 10 to the power minus 3. That equals to minus 790 for the gradient. Now that we have calculated the gradient, we now know from the equation of the line ln K equals minus EA, activation energy over R, times 1 over T plus ln A. The gradient in this case is minus EA over R equals to M, which is minus 790. And therefore, I can then say, well, the minus will cancel out. So A is 790 times R, but R is 8.31. And that equals to 6564.9. But the answer is looking for 3 significant figures. We would write that to be 6560. The activation energy is 6560 joules per mole. Part 2. Use the graph to calculate the value of pre-exponential factor A. Show your working. Well, from the graph, we know that, well, from the equation of the straight line, we know that ln K equals minus EA, activation energy over R, times 1 over T plus ln A. But we can say that this is compared to Y equals mx plus C, where we can see that C is ln A. Ln A equals to 31.25. That's the value of C. And therefore, I can convert ln A back into log base. So that's log base E of A equal to 31.25. Therefore, if I raise E to the power of 31.25, and the answer will be equal to A. Therefore, I have E to the power of 31.25 equals to A. A equals 3.73 times 10 to the power 13. A here as 3.73 times 10 to the power 13. Intercept here is that value here. So that's 31.25. And that's what we've got here. And then from there, we're able to calculate A, the pre-exponential factor. Question 18. Nitrogen monoxide, NO, and oxygen gas, O2, react to form nitrogen dioxide, NO2, in the reversible reaction shown in equilibrium 18.1. Write an expression for Kc for this equilibrium and state the unit. So for Kc, the numerator is NO2 concentration squared, and the denominator is NO squared times O2, and the unit will be, well, we got the concentration squared over concentration cube, so that will be the squared in numerator. We cancel out the squared in the denominator concentrations, so you're going to get 1 over concentration, and 1 over concentration is going to be decimeter cube per mole. Why? It's because we have the mole per decimeter cube all squared over mole per decimeter cube squared and mole per decimeter cube. That was cancel that one. We're going to get 1 over mole per decimeter cube, and that will give you decimeter cube per mole. Part B. A chemist mix together nitrogen and oxygen and pressurizes the gases so that their total gas volume is 4.3 decimeter cube. The mixture is allowed to reach equilibrium at constant temperature and volume. The equilibrium mixture contains 0.4 mole of nitrogen oxide and 0.8 mole of oxygen gas. Under this condition, the numerical value for Kc is 45. Calculate the amount in mole of NO2 in the equilibrium mixture. We have these gases here as 2NO plus O2, and that, because it's in equilibrium, it gives 2NO2. Well, 3 formulas, but the first one we're going to use is, we know that concentration is mole over volume, and mole will be equal to concentration times volume. The first case is we need to find the mole in this case, and the mole we're given for NO is 0.4, and the mole for oxygen is 0.8, and NO2 is what we're looking for. We know the total volume in this situation is 444, and now we can find the concentration, and concentration, we can see concentration is mole over volume, and therefore the concentration in this case will be 0.1. That's because we get 0.4 divided by 4. So if I draw a line here, that shows how we get the concentration. So concentration is 0.4 divided by 4, that's 0.1. 0.8 divided by 4 will be 0.2. As you know, concentration is mole over volume. And now what we need to do is apply the Kc. Kc is equal to the concentration squared of NO2 over concentration of NO squared and O2. What we now need to do is rearrange that and plug the values in to find NO2. For NO2 concentration will be the square root of Kc times the concentration of NO squared times the concentration of O2. The square root of 45 times the concentration of NO squared, which is 0.1 squared, times the concentration of O2, which is 0.2, and that gives 0.3. That's the concentration of NO2. NO2 concentration is 0.3 mole per decimeter cube. Use that to calculate the mole. In this case, we know the concentration is 0.3. To calculate the mole, using the formula here, so we can write the concentration for NO2, which is the mole for NO2, will be equal to 0.3 times 4, and that is 1.2. This value here will be 1.2, and we can write it also here. The amount means mole, is 1.2. Part C. The values of Kp for equilibrium 18.1 at 298 Kelvin and 1000 Kelvin are shown below. Predict with a reason whether the forward reaction is exothermic or endothermic. What we're going to look at is the trend here. The Kp value decreases as the temperature increases, and therefore we need to know what Kp is. Kp is the total partial pressure of the product divided by the total partial pressure of the reactant. And you can see for the Kp to decrease, what that meant is that the denominator is bigger than the numerator, then Kp will decrease. And for that meant that the reactant is bigger than the product, so that means more reactant is being produced, because more reactant is being produced due to increase in temperature, and this can only happen in exothermic reaction. So we can say that the Kp decreases as the temperature increases, and this is due to increase in the reactant and decrease in product. This is exothermic. This can only happen in exothermic reaction, where the forward reaction is favored by the decrease in temperature. But the temperature has increased, that favors the backward reaction, which is what's happening here, and so that's exothermic. Part 2. The chemist increases the pressure of the equilibrium mixture at the same temperature. State and explain in terms of Kp how you would expect the equilibrium position to change. Well, first of all, we have the equation that says that we go 2NO plus O2 given the 2NO2, and if we count the total number of mole of the stoichiometric mole, so that's 2 plus 1, and that's 3 moles, or if you like, let's just write 3 moles, and that is given 2 mole. So what we've got here is that there are more collision from the reactant, and because the more of the reactants are colliding, because there are more of them, and there's more because there are 3 of them compared to 2, so these are more colliding, and therefore they'll be producing more product. So the equilibrium will shift to the right. The equilibrium position will shift to the right, so the ratio in Kp, because we know what Kp is, so Kp is the total partial pressure of the product divided by the total partial pressure of the reactant, and that's what Kp is. That ratio of the partial pressure is what we're talking about. In Kp expression decreases, so the ratio will increases to restore Kp back to equilibrium. Question 19. This question is about acids and bases found in the home. A. Ethanoic acid, CH3COOH, is the acid present in vinegar. A student carries out an experiment to determine the pKa value of CH3COOH, ethanoic acid. The concentration of ethanoic acid in vinegar is 0.870 mole per decimeter cube, and the pH of ethanoic acid is 2.41. 1. Write the expression for the acid dissociation constant Ka of CH3COOH. Expression for the dissociation of ethanoic acid, H plus aqueous plus CH3COO minus aqueous. Ka value, that will be concentration of H plus times the concentration of CH3COO minus divided by the concentration of the acid. Part 2. Calculate the pKa value of CH3COOH. Give your answer to 2 decimal places. We're looking for pKa value. That means we need to find the Ka value. And we know that the Ka value is concentration of H plus times the concentration of CH3COO minus divided by the concentration of the ethanoic acid. Now, because this is a weak dissociation, the concentration of H plus is equal to concentration of CH3COO minus. Therefore, we can then rewrite the Ka value as Ka equals H plus concentration all squared divided by concentration of CH3COOH. But first, we need to find the concentration of H plus. We know the pH, which is equal to minus log of base 10 of concentration of H plus. Therefore, we can rewrite the concentration of H plus to be equal to 10 to power minus pH, which in this case is 10 to power minus 2.41, because the pH is equal to 2.41. That's given. And that will be the concentration of H plus, and that concentration of H plus equals to 3.89 times 10 to power minus 3 mole per decimeter cube. Now we know the concentration of H plus. We can then plug that in to find the Ka value. Will be the concentration of acid H plus, 3.89 times 10 to power minus 3 all squared, divided by the concentration of ethanoic acid, which is 0.870, and therefore Ka value will be equal to, in this case, 1.74 times 10 to power minus 5 mole per decimeter cube. And we can find the pKa value. So pKa is equal to minus log of base 10 of Ka value, which means it's minus log of base 10 of 1.74 times 10 to power minus 5. So that's pKa, and that value will become 4.76 to 2 decimal places, 4.76. Part 3. Determine the percentage dissociation of ethanoic acid in the vinegar. Give your answer to 3 significant figures. Well, we need to know what percentage dissociation is. Percentage dissociation is equal to the concentration of H plus divided by the concentration of the acid, in this case ethanoic acid, times 100. And we know what the concentration of the H plus is, 3.89 times 10 to power minus 3, divided by the concentration of the acid, which is 0.87 times 100, and that equals to 0.447%. Right, 0.447% to 3 significant figures. 1, 2, 3. 0 point is not a significant figure, so 1, 2, 3 is 3 significant figures. Part B. Many solid drain cleaners are based on sodium hydroxide, NaOH. A student dissolves 1.26 grams of a drain cleaner in water and makes up the solution to 100 centimeter cube. The student measures the pH of the solution as 13.48. Determine the percentage by mass of NaOH in the drain cleaner. Give your answers to 3 significant figures. So the first point is, I think we need to find the concentration of the H plus. Once we know the concentration of the H plus, we can then find the concentration of the OH minus. And if we know the concentration of OH minus, then we can find the mass of sodium hydroxide. And then finally, we can find the percentage of sodium hydroxide. Because we want to determine the percentage by mass, we need to determine the percentage by mass of sodium hydroxide. Number 1, we need to find concentration of H plus. And to do that, we know that pH is given to us as minus log of base 10, concentration of H plus, and that value is 13.48, which is H plus equals 10 to power minus 13.48, and that gives us the H plus concentration to be equal to 3.31 times 10 to power minus 14 mole per decimeter cube. Now we need to find number 2, we need to find the concentration of OH minus. And to find the concentration of OH minus, we need to use the Kw, which is concentration of H plus times the concentration of OH minus, and that equals to 10 to the power minus 14. And that equals to 1 times 10 to the power minus 14, which means that the concentration of OH minus will be equal to Kw, which is 10 to the power minus 14, divided by the concentration of H plus. I can put that here. OH minus concentration will be 1 times 10 to the power minus 14, divided by 3.31 times 10 to the power minus 14. Don't forget the concentration is always mole per decimeter cube. The concentration of OH minus will be equal to 0.302 mole per decimeter cube. Now that we've found the concentration of OH minus, we can now find the mass of sodium hydroxide. So number 3 will be to find the mass of sodium hydroxide. And to do that, we could now, to find the mass, we know that mole equals concentration times volume. And that mole is also equal to mass over relative molecular mass. And therefore, we know the mass that we're looking for will be equal to concentration times volume times relative molecular mass. And in this case, that mass will now be equal to, we know the concentration is 0.302 times the volume. We know what the volume is 100 centimeter cube, 100 divided by 1,000, and then times the relative molecular mass of sodium hydroxide, which is 23 plus 16 plus 1, so that would be 40 grams per mole. Sodium hydroxide is 40 grams per mole. That's calculated from the periodic table, and altogether that gives 1.21 grams. Fourth thing we could do is to find percentage of sodium hydroxide. And to find the percentage, we need to find the mass dissolved. We know the mass dissolved is equal to 1.26 grams. Here is 1.26 grams. And the mass of sodium hydroxide is 1.21 grams. And therefore, the percentage mass will be 1.21 over 1.26 times 100, and that equals 95.9%. We need to write that to 3 significant figures. That would be 95.9%. Finding the concentration of H plus, that concentration of H plus can be found by writing H plus equals to 10 to the power minus pH. So that's the formula we've used here, because we just convert this. We know how to convert it actually. If you do, you go to raise that, multiply both sides by minus, and then you raise that to the power of that, and the answer will be concentration. So that's how we found it. We multiply both sides by the minus, so you're going to get minus pH log 10 of concentration of H plus, and then you raise 10 to the power of minus pH, and the answer will be concentration of H plus. So that's how we find that. So that's how that became that. Secondly, we've used the Kw here. Kw is in the data booklet, where Kw equals to 1 times 10 to the power minus 14, and that's the concentration of H plus times the concentration of OH minus. So that's found from the data booklet. We also use the periodic table to work out the molar mass of sodium hydroxide, which is the molar mass of sodium hydroxide is 40 grams per mole. We also used the mole equation. There are 2 mole equations here that we've used. Mole is equal to concentration times volume. That's one equation. Mole is also equal to mass weighed over the relative molecular mass. The relative molecular mass is the mass from periodic table that you work out from the periodic table. Those are the 2 equations we've used together. So therefore, the concentration times volume equals mass over relative molecular mass. And to find mass, we multiply both sides by the relative molecular mass. So that's why we got that. C part. Sodium carbonate Na2CO3 is a base used in washing powder. Sodium carbonate contains the carbonate ions CO32- shown below. Draw the dot and cross diagram for the carbonate ion. Show outer electrons only and use different symbol for electrons from carbon and oxygen and any extra electrons. To draw the structure, we start with carbon, and so if we have carbon here, carbon itself is 12,6 and it's got the electron configuration of 1s2, 2s2, 2p2, and the outer electrons. So this is a shell we're drawing. We're drawing the second shell. That's the valence shell. That's where the valence electrons are. The valence electrons are the outer electrons, and the valence shell is the outer shell. For oxygen, we have oxygen, and that's 16,8, and that is 1s2, 2s2, 2p4. Again, this is the valence shell. That's the outer shell. Valence shells are the outer shell, and the electrons in oxygen is 6. So we're going to start with one carbon, a dot for carbon, and a cross for oxygen. So that's O there. And another dot for carbon and a cross for oxygen. That's O there. And oxygen will have 2 electrons there, 2 pairs of electron, and another electron with a vacant electron. That's why it's negative. And likewise, it will have a pair of electron, another pair of electron, a negative electron, and the vacant electron. We've got another double bond here, which is carbon, oxygen, O there. And this double bond has just 2 pairs of electrons. If we count the number of electrons in that shell, should be 8, 8, 8. And because it's got 1 vacant electron there, 1 vacant electron there, that's negative. So that means we have to put this in a square bracket like that to indicate a negative. So that's 2 minus 1 for that and 1 for this one. If we count, it should be 8. 1, 2, 3, 4, 5, 6, 7, 8. That's correct. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. The cross is the oxygen electron, and the dot is the carbon electron, and the vacant is the vacant space where sodium electron will be when it binds with 2 sodium here. Question 20. This question is about the halogen group of elements and some of their compounds. A. The halogen shows trends in their property down the group. The boiling point of these halogens are shown below. Explain why the halogen shows this trend in boiling point. As we go down the group, the number of electrons increases, hence the London forces will also increase, and more energy is needed to break the London forces, which are called Van der Waals force, which is induced dipole-dipole interaction. Part B. Hydrogen iodide, Hi, is decomposed by heating into its element. 2Hi gas gives H2 gas plus I2 gas. The decomposition is much faster in the presence of a platinum catalyst. Complete the enthalpy profile diagram for this reaction using formulae for the reactant and product. Use EA to label the activation energy without a catalyst. Use EC to label the activation energy with a catalyst. And use delta H to label the enthalpy change of reaction. So I'm going to draw the energy profile here, and I'm going to start with the reactant. That's the reactant, and finish up with the product. So that's the product. How do I know the product is there? Well, because the delta H here is positive, If it's positive, the product is above the reactant, and this is called endothermic. If it's negative, it will be below reactant, and it will be exothermic. What I need to do is draw the energy profile from the reactant to the product and draw another energy profile. This time it is with catalyst. This is the reactant. We measure everything from the reactant, and this is product. We know it's going to be endothermic. The distance from the catalyst activation energy, and this one is the activation energy without the catalyst, and we need to also measure the delta H, which is from the reactant to the product. So that's delta H, and that's plus 9.5 kilojoules per mole, and that's endothermic, 2HI gas, and a product H2 gas plus I2 gas. Part C. Compound A is an oxide of chlorine that is a liquid at room temperature and pressure and has a boiling point of 83 degrees Celsius. When 0.4485 grams of A is heated to 100 degrees Celsius at 1 times 10 to the power 5 Pascal, 76 centimeter cube of gas is produced. Determine the molecular formula of compound A. Show all your working. What are we given? We are given the temperature, which is 100 degrees Celsius plus 273 to become 373 Kelvin. We're given volume, which is 76 centimeter cube. The centimeter implies that this is 76 over 100, and because it's cube, so you have to cube it, and that's meter cube. So that's what I meant, because centimeter is 1 over 100, and that's 1 over 100 cube, and that will become 76 over 10 to the power 6 meter cube, which is 76 times 10 to the power minus 6 meter cube. That's the volume that we're given. We're also given the R value. R value is 8.314 from the data booklet, and we know the pressure P is 1 times 10 to the power 5 Pascal. We know the mass M is 0.4485 grams. First, we need to use PV equals nRT, and we need to find the mole. Therefore, N is a mole, which is PV over RT. N equals 1 times 10 to the power 5 times 76 times 10 to the power minus 6 divided by 8.314 times 373, and that gives us a value of 2.45 times 10 to the power minus 3 mole. Now, if we know N, we can find the M. So let's find M, the molecular mass. The molecular mass is basically, we know that N equals big M, mass weight, over relative molecular mass, which implies that relative molecular mass is M over N, 0.4485 divided by 2.45 times 10 to the power minus 3, and that equals to 183 grams per mole. So now we know the relative molecular mass, but for chlorine, we need to know common oxidation state of chlorine. So for chlorine, the common oxidation state are +1, +5, +7. We can get, they are Cl2O, and we can get Cl2O5 and Cl2O7. And the relative molecular mass for Cl2O is 87, and for Cl2O5 is 151 grams per mole, and for Cl2O7 is 183 all grams per mole. What we're looking for is the Cl2O7, because the mass for that is what we've calculated is 183 grams per mole. So the chlorine is 35.5. 35.5 times 2 is 71. 71 plus 16 is 87. 71 plus 16 times 5 is going to be 151. 71 plus 16 times 7 is 183. The oxidation state of +1. Yes, because oxygen is -2. And for the whole thing to be 0, if oxygen is -2, because oxygen has a higher electronegativity, so it will take up its negative oxidation state. So that's -2, which meant that this has to be +1, because +1 times 2 is +2. +2 minus 2 is 0, so that's good. Oxygen is -2. -2 times 5, -10. And if this is 2, this has to be +5 to be 0, because 2 times 5 is 10 to be 0. Likewise, -2 times 7 is -14. For it to be 0, that has to be +14. And below 2 of them has to be +7. This is how we know the oxidation state here. But these are common, and it's expected to be aware of those, and that's the answer. Part D. Compound B is an iodate 5 salt of a group 1 metal. The iodate 5 ion has the formula IO3-. A student carry out a titration to find the formula of compound B. Step 1. The student dissolves 1.55 grams of B in water and mix up the solution to 250 cm3 in a volumetric flask. Step 2. The student pipettes 25 cm3 of the solution of B into a conical flask, followed by 10 cm3 of dilute sulfuric acid and an excess of Ki aqueous. The iodate 5 ions are reduced to iodine as shown below. Step 3. The resulting mixture is titrated with 0.15 mole per decimeter cube N2, Na2, S2O3 aqueous. The student repeats step 2 and 3 until concordant titer are obtained. 1. Complete the table 20.1 and calculate the mean titer that the student should use for analyzing the result. Work out the difference between final and initial, and this one will be 24.00 and this one will be 23.40 and this is 23.75 and this one will be 23.85, and we need to complete the table and work out the mean titer. So what are we going to use here? The concordant titer that we're going to use are that and that, and when you add them together, so we're going to do 23.75 plus 23.85 divided by 2, and that will give 23.80. The mean titer will be 23.80. The reason why I've chosen these two values are because they're closer together, and we have to use something called a concordant titer, and the concordant titer has to be between plus or minus 0.10 centimeter cube of each other. So you can see that the difference between this one are very close in that range compared to the difference between this and that, and the difference between this and that, and even that. So these are the two concordant titers that we're going to use, and that's why we've used them here. Part 2. The uncertainty in each burette reading is plus or minus 0.05 centimeter cube. Calculate the percentage of certainty in the titer obtained from titration 1. Give your answer to 2 decimal places. First, we need to find the uncertainty, and the uncertainty is 0.05, and we have to multiply by the number of times we've used it, which is twice, because we take the initial and the final reading, and then we obviously divide it by the value we obtained from titration 1, which is, if we go back to titration 1 here, is 23.4, and so we write 23.4 down, and then we times it by 100 uncertainty, and that will be equal to 0.43 down here. Part 3. Describe and explain how the student should determine the endpoint of this titration accurately. In this part, the student should add starch near the end point. And then you get a blue, black to colorless. We added starch near the end point, and starch is our indicator, and the color change is from blue-black or blue or black to colorless. Part 4. Determine the relative formula mass and formula of the group 1 iodate 5B. Show your working. First of all, the iodate ion that we used was I3- plus acidified, so 6H plus, and plus 5 iodine minus, and that gave us 3I2 plus 3H2O, and the thiosulphate 2S2O3 2 minus plus I that was produced I2 to then give S4O6 2 minus plus 2I. If we're getting 3 from the iodine here, we need to make that 3 as well. We're going to times it by 3. So by timesing it by 3, we're going to get 6S2O3 2 minus plus 3I2. But that will disappear, the 3I2, when we add them together, 3I2, to give 3S4O6 2 minus plus 6I minus. Because don't forget that that's I minus as well, so that's I minus there. Call that equation 1, and let's call this equation 2. We add 1 plus 2 together, what would we get? We get 6S2O3, because the 3 I's, 3I2 we cancel out. We're going to get plus IO3 minus plus 6H plus 5I minus, and that would go to 3S4O6 2 minus plus 6I minus plus 3H2. From there, we can calculate the number of mole of S2O3 2 minus, and that will be concentration times volume. That will give, we know the concentration is 0.15, that was given, times the volume, which is 23.8 from the titer, divided by 1000, and that gives 3.57 times 10 to power minus 3 mole. We are given these reaction equations. This 2 is what we know, but we're making 3 iodine and we're only using 1, so make sure we use 3 times this by 3 to make that the same, times the whole lot by 3. And that's why we got this, to form equation 2, because we times those 1 by 3 and we get this. Okay, now that we've got that, what we want to do now is add the equation 1, this one, and equation 2 together, the new equation that we formed, and eliminate the commonality. The common factor here is 3 iodine and 3 iodine, so that's gone. So we only have this left. And now if you look at the ratio 6 to 1, so this one is 6 times that one. So if you want to find the mole of this, we need to divide the mole of thiosulphate, this one, by 6. That will give us the mole of iodate 5. The reason why it's called iodate 5 because the oxidation number is 5. If this is minus 2, overall charge is, oxygen is minus 2, overall charge is minus. So that needs to be plus 5 because minus 2 times 3 is minus 6, and the overall charge is minus. So you need that to be plus 5. Plus 5 minus 6 will give you minus 1. So that's why this is iodate 5. So we need to calculate the number of mole of iodate 5 in the ratio. If this one is 6 times, so we need to divide this one by 6 to get the number of mole of that. So the mole for the NiO3 minus mole will be the 3.57 times 10 to power minus 3 divided by 6, and that is equal to 5.95 times 10 to power minus 4 mole. But this mole is the number of mole in 25 centimeter cube. Now we want to find the mole in 250 centimeter cube, so we need to times it by 10. NiO3 minus in 250 centimeter cube will be equal to 5.95 times 10 to power minus 3 mole, because we times it by 10. because this was in 25 centimeter cube. The molar mass equal to the mass over mole, and that equals to, we know the mass because we're given, it's 1.55 divided by the mole, which is 5.95 times 10 to the power minus 3. That equals to 260.5 grams per mole. Formula for B, MiO3, it's going to be group 1 because the IO3 is minus and group 1 is plus 1. That altogether add up to 260.5. But we know the relative molecular formula for iodine is 127. Oxygen is 16 times 3 is 48. Let's put it there. If this is 127 and that is 48. Now, what do we get? Then we can find M easily. M will be equal to 260.5 minus 127 minus 48. That will be equal to 85.5 grams per mole. And what's closer in, if you're looking at periodic table, group 1 that has a relative molecular mass of 85.5, it's rubidium. Rb is M, which is 86 grams per mole. So the formula of B is rubidium IO3, and the relative formula mass is 260.5 grams per mole. Okay, so we've got M iodate 5, and that's solid, and it dissolves in water to form M plus iodate 5 ion, which is aqueous and aqueous. The reason why we call it iodate 5 is because we've got the overall charge of -1, and the oxygen is -2. -2 times 3 is -6, and that's iodine. And so iodine will become -1 plus 6, and that is plus 5. Hence we call it iodate 5. In this case, M plus is a spectator species, and the point of this experiment is to find what M is. Okay, so we've got 1.55 grams dissolved in water. We transfer that into a beaker of water, and that's 1.55 grams. And then from there, we transfer that into a volumetric flask and mark up to 250 centimeter cube. And then we pipette 25 centimeter cube into a Lemire flask or conical flask. And then we add 10 centimeter cube of sulfuric acid plus excess potassium iodide solution. At this point, we've created an equation for this reaction, which is the iodate 5 aqueous plus H plus, that's acidified with sulfuric acid, and then we add potassium iodide. That should give us iodine plus H2O. But how many water did we form? There's 3 oxygen here, there's 1 there, so we need to multiply that by 3. We've got 6. 2 times 3 is 6, so we've got 6 hydrogen there plus. And if we balance the charge, the charge here is 0, and this one is overall charge is -1 plus 6, that's plus 5, and we want 0, so we need -5. So if you times that by 5, that will be the -5. So if you can see that plus 5, so the charge is now balanced. So the final equation that we've created here is IO3 minus, it's aqueous, plus 6H plus 5 iodide, aqueous as well, that's aqueous, and that will give I2 plus 3H2O. We can check if it's balanced. 3 oxygen there, 6 hydrogen there, 1 iodine plus 5 iodide. So we need to balance this one by adding 3, because that is now 3 times 2, 6. 5 plus 1 is also 6. So that's balanced. So the next stage is to titrate that. So we're going to titrate that with sodium thiosulphate. Now, thiosulphate is also a solid. When dissolving in liquid to form the solution, the sodium, we form 2 sodium plus, that's aqueous, plus S2O3 2 minus, that's aqueous. So you're going to form those ions. And the sodium here is expected to species, just like this is expected to species. That means it's not taking part in the reaction. And the iodide here, if you look at the potassium itself, a solid, when dissolved in liquid, we also form potassium plus iodide. Again, that is expected to species here. That's why we've got the I here from there. And the H plus is from the acid. That's where H plus is from. And then you got the iodate 5 from there. So now we're using a solution of sodium thiosulphate, which is dissolved in water. And what's going to be reacting now is the thiosulphate. Now we're going to react thiosulphate with the iodine that is being produced here in this solution here. The iodine is being produced. We're going to react with thiosulphate. So don't forget the aqueous. By the way, that's aqueous. That's aqueous. So now we're going to titrate that with this. And the titrant, the titer from the titration, the titer is 23.8 centimeter cube, where we've added starch, which monitors the reaction of iodine with the thiosulphate. And when that finishes, then we have color change from a black or blue to colorless. So that's what the indicator is here, is to add starch, and the starch will react with iodine to form a black, but when the iodine is being used up, it will then turn colorless. And that shows that all the iodine is being used up. Okay, so don't forget the equation we got is IO3 minus plus 6H plus 5I minus, that goes to I2, 3 of those, plus 3H2O. But the thiosulphate, when added, will be S2O3 2 minus plus iodine, because the thiosulphate is now reacting with the iodine. And we know that this one you have to remember, S4O6 2 minus, that's forming a dimer, plus I minus. So converting the iodine back to iodide. So obviously there's 2 iodine there, so that'll be 2 there. And because of the dimer, this will be 2. Since that is forming that, then that will be times 2. 2 times S, 2 times 2 is 4. 2 times 3 is 6. You can see this is a reduction because the iodine is going from 0 to -1. So that's reduction here. This is reduction, that's oxidation. And because it's redox, we need to find the overall reaction, which means we draw a line here. Now, before we can do that, we need to see there's 3 iodine here and there's 1. So we need to multiply everything by 3. And by doing so, we just need to times that by 3. So that will become 6. And this will become 3, 3, and 6. Now we have the same number of iodine here and there. We can add up these overall. If we add them up, we're going to get 6S2O3 2 minus plus IO3 minus plus 6H plus 5I minus, which would then give 3S4O6 2 minus plus 6I minus plus 3H2O. The stoichiometric mole of these is 6 to 1. If we know the mole of these, to find the mole of that, we'll divide the mole of these by 6, because this is 6 to 1. And we do know the mole of these because we're given that mole is N of S2 as S2O3 2 minus, that mole is concentration times volume, and the concentration is 0.15, and the volume used is 23.8 divided by 1000 to convert it into decimeter cube. So that's concentration times volume, and that gives a value of 3.57 times 10 to power minus 3 mole. The mole, because that's the mole of thiosulphate in 25 centimeter cube here, I need to find the mole of iodate 5. We need to divide that by 6, so we can say the mole of IO3 minus will be 3.57 times 10 to power minus 3 divided by 6, and that is 5.95 times 10 to power minus 4 mole. Now we know the mole of iodate in 25 centimeter cube that reacted 25 centimeter cube, and let's transform that into 250 centimeter cube that it's in the volumetric flask. And to do that, we have to times it by 10. And so this mole, we have to transform it into the volumetric flask mole. So we times that by 10. So that would be 5.95 times 10 to the power minus 3 mole. If that's the mole of IO3 in 250, we can find the mass. The mass we want to find is relative molecular mass. We know mole is mass over relative molecular mass, and therefore relative molecular mass is mass over mole. We know the mass is 1.55. That's what we dissolve in 250 centimeter cube of water. We divide it by the mole, which is 5.95 times 10 to the power minus 3, and that gives 260.5 grams per mole. The mass of MiO3 altogether is 260.5 grams per mole, but we know that iodine is 127, oxygen is 16 times 3 is 48. Now we can find M, which will be 260.5 minus 127 minus 48, and that is 85.5 grams per mole. And we know M is in group 1 because it's M plus. If we go back here, we know that's M plus, and plus 1 is group 1 of the periodic table. In group 1, go down to find the mass, which one has a mass of 85.5, and that turned out to be rubidium, which is 86 grams per mole. Therefore, the compound we use in this experiment is RbIO3, and it has a relative molecular mass of 260.5 grams per mole. Question 21. This question is about some reactions of D block elements in their ions. Table 21.1 shows standard electrode potentials which will be needed within this question. A. Complete the electron configuration of nickel atom and nickel 2+ ion. Nickel in the periodic table, and the relative atomic mass is 59. So we're writing the electron configuration here. So 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2 and 3d8. When it loses 2 electrons, it will become, the 2 electrons will be lost from 4s2. The electron configuration will be 2s2, 2p6, 3s2, 3p6, 3d8. The 4s is filled before the 3d, and when it's losing, it loses the 4s first before the 3d. B part. A standard cell is set up in the laboratory with the cell reaction shown below. Nickel solid plus iodine aqueous react together to give nickel 2+ aqueous plus 2 iodide aqueous. I. Draw a label diagram to show how the cell could be set up to measure its standard cell potential. Include details of apparatus, solutions, and the standard condition required. So we have 2 half cells, each with electrolytes, and insert 2 solid electrodes, and the 2 electrodes are connected by a voltmeter, and the 2 electrolytes are connected by a salt bridge, and a salt bridge is a filter paper with potassium nitrate electrolyte. And to determine what the electrodes are, we look at the reactant. One of them is a solid nickel, so we can use a solid nickel electrode, and with a nickel 2+ aqueous solution electrolyte, so that would be nickel sulfate. And the iodine is liquid. We cannot use a liquid electrode, so we have to use platinum, and we have the electrolytes will be iodine aqueous and iodide aqueous, and we need to label the salt bridge. The standard condition will be 1 mole per decimeter cube at 298 Kelvin. Part 2. Predict the standard cell potential of this cell. From the table 21.1, nickel 2 plus, we're looking at that potential here, and nickel 2 plus is minus 0.25 volts, and we're looking at the iodine as well, and that is plus 0.54. We want to keep the more positive and take away the more negative or the less positive. The more positive is the iodine one, which is 0.54, and you want to take away the less positive, which is minus 0.25. In this case, minus is plus, and that will give you 0.79 volts. Always keep the more positive if you want to work out or predict the potential of the two half cells, which is a full cell. You keep the more positive and you take away the less positive, and that's your potential cell. Part C. Use the information in table 21.1 to help you answer both parts of this question. 1. Write the overall equation for the oxidation of iron 2 plus by acidified hydrogen peroxide H2O2. Okay, so we're looking at iron 2 plus is going to be oxidized to iron 3 plus by acidified H2O2. This is iron 3 plus gaining electron and reduced to iron 2 plus, hence the standard reduction potential. So this is just showing the reduction process here. And that's why the potential is standard reduction potential, because they're gaining electrons, so they're being reduced. But the iron 2 is going to be oxidized. But if we look at the electrode potential for peroxide, hydrogen peroxide here, it is plus 1.78. This is more positive. This will stay compared to the iron potential, which is 0.77. So this is less than that. This will go backward. In this case, this will go backward and this will go forward, which means that we can rewrite this equation by saying, well, iron 2 plus will be losing electron to become iron 3 plus E minus, and the peroxide will stay because it's got a higher potential. It will be H2O2 plus 2H plus. It will be gaining 2 electrons going forward to 2 water. In that case, we need to, in order to balance the number of electrons, this is gaining 2, we need 2 from iron. We need to multiply that by 2. Now if we've done that, we can draw the overall equation here, and that would be H2O2 plus 2Fe2 plus 2H plus will be going to 2Fe3 plus 2H2O. And if we notice, the 2 electrons will cancel out because both are in the opposite direction of the arrow. One is there, they cancel out. Because there will be 2 electrons here, 2 electrons here, and they will cancel out. This will be the reaction, the overall reaction of this oxidation. C, part 2. Zinc reacts with acidified Cr2O72-, that is dichromate, to form Cr2 plus ions in 2 stages. Explain why this happens in terms of electrode potential and equilibria. Include overall equation for the reactions which occur. But let's look at this situation we're looking at here. We're going to look at 3 situations. This one, zinc is reacting with that, and zinc reacting with that. That's the potential for dichromate. And if you look at the potential, it's plus 133 volts. Now, that is higher than that of zinc, which is minus 0.76. This will stay because it's more positive. This is less positive, so it will reverse. What we can do now is we're going to release the electron. This one needs 6 electrons, obviously, and this is giving out 2 electrons. Obviously, we have to multiply that by 3 to make it 6 electrons. Zinc is now going to be reversed. We'll be losing 2 electrons to zinc 2 plus 2 electrons. But the dichromate needs 6 electrons. We need to multiply that by 3 to get the 6 electron. 3 zinc going to 3 zinc 2 plus 3 times 2, 6 electrons. Now we can write the dichromate down. The dichromate is Cr2O72-. It's acidified, so it's 14H plus the 6 electrons, then go forward to 2Cr3 plus, plus 7H2O. You can write the overall equation for that. That electron will cancel that electron, and therefore the overall equation will be dichromate 2- plus 3 zinc plus 14H plus. That will go to 2Cr3 plus zinc 2 plus 7 water. That will be the overall equation that we need to write between zinc, which is that zinc, and dichromate. We need to do the same with zinc and chromium ion. If we look at chromium ion is minus 0.42 and zinc is minus 0.76. The more positive is minus 0.42. That stays, and zinc will have to be reversed. But how many electrons does chromium ion need to gain to become Cr2+? It needs just 1 electron, but zinc is going to release 2 electrons, so we need to multiply that by 2 because the number of electrons has to balance out. Write the electron release first by zinc going to zinc 2 plus 2 electron. Now we can write the chromium, which will stay Cr3 plus, gaining 1 electron to become Cr2 plus. We're releasing 2 by zinc. We need to multiply all this one by 2. 2, 2, 2. And now we can write down the overall equation for that one. Overall equation, zinc plus 2 Cr3 plus. We go on to zinc 2 plus 2 Cr2 plus. And that's the overall equation. In both cases, the more positive potential stays and less positive reversed, meaning more positive shift right and less positive shift left. Part D. 3 different reactions of copper compounds are described below. Reaction 1. Aqueous copper sulfate reacts with excess aqueous ammonia in a ligand substitution reaction. A deep blue solution is formed containing an octahedral complex ion C, which is a trans isomer. Reaction 2. Copper 1 oxide reacts with hot dilute sulfuric acid in a disproportionation reaction. A blue solution D and a brown solid E are formed. Reaction 3. Copper 2 oxide reacts with warm dilute nitric acid in a neutralization reaction to form a blue solution. Unreacted copper 2 oxide is filtered off and the solution is left overnight in an evaporating dish. A hydrated salt F crystallizes with the percentage composition by mass: copper 26.29%, hydrogen 2.48%, nitrogen 11.59%, oxygen 59.63%. Identify C to F by formulae or structures as appropriate. Include equations, any changes in oxidation number and working. Copper 2 sulfate reacts with excess aqueous ammonia in a ligand substitution reaction, and deep blue solution is formed containing an octahedral complex ion C, which is a trans isomer. Well, in this case, for the copper 2, we're looking at copper and with water, so hydrated, 6 of those because it's octahedral and it's 2 plus, that's copper 2 plus. And if we're reacting that with ammonia, NH3, and we would get a substitution of a deep blue solution, so copper NH3, we are going to be getting 4 of those, and H2O, there will be 2 of those, we need 4 of those, and that obviously will be releasing 4 water because we're substituting for ammonia, so for H2O, and the charge on this will be still the same. I'm expecting that to be 2 plus, and if we were to draw that complex, copper will be in the center and got ammonia here, NH3. We got another ammonia there. There's 4 ammonia, NH3. 3, and it's a trans. We got another ammonia there, NH3, and another one there. That'll be NH3, and I've got water up here, H2O, and another water, H2O, and these will have a positive charge of +2. That will be for reaction 1. Now for reaction 2. For reaction 2, copper 1 oxide reacts with hot dilute sulfuric acid in a disproportionation reaction. A blue solution D and a brown solution E are formed. The first reaction, this is C. Now we're going to, for copper 1 oxide, will be CU2O, and that will decompose into copper 2 plus copper 0. This is copper 1 plus and copper 2 plus and copper 0. Copper 1 plus and plus H plus acid, and that we go on to copper 2 plus copper plus H2O. And if we to write that down, copper 2O, that's copper 1 plus sulfuric acid, H2SO4, going to form copper sulfate, that's copper 2 plus copper solid plus water. D is copper sulfate and E is copper. Reaction 3. Copper 2 oxide reacts with warm dilute nitric acid in a neutralization reaction to form a blue solution. Unreacted copper 2 oxide is filtered off and the solution is left overnight in an evaporating dish. A hydrated salt F crystallizes with the percentage composition by mass: copper 26.929%, hydrogen 2.48%, nitrogen 11.59%, oxygen 59.63%. We need to identify F. So write down the equation for copper 2 oxide, CuO, plus nitric acid, HNO3, reacted together to form copper nitrate, that will be 2, plus H2O. Balancing this equation, we required 2 of those because I've got 2 nitrates. There's 2 there of nitrates, so 2 times the nitrates. Then 2 hydrogen here, 2 hydrogen there, and 1 oxygen here, 1 oxygen there, 1 copper, 1 copper. That's balanced. This must be the blue solution, and that's copper NO3 2.XH2O, which is the hydrated copper nitrate. What we need to do is find the composition of this hydrated copper nitrate. We've got copper and hydrogen, nitrogen, oxygen. Those are the 4 elements involved here: copper, nitrogen, oxygen, hydrogen. We've got the percentage. Copper is 26.29, hydrogen is 2.48, and nitrogen is 11.59, oxygen is 59.63. Divide that by the relative molecular mass, that is 63.5. That is 1.0 to 1 decimal place. Nitrogen is 14.0 and oxygen is 16.0. 0.414. This is 2.48, and this one is 0.828, and this one is 3.727. And we need to divide by the smallest, everything by the smallest. So the smallest here is 0.414, everything by 0.414. So 0.414 divided by 0.414, divide that by 0.414 and divide that by 0.414. We're going to get 1, that's the ratio now, and into that one is 6, that's the ratio, and this is 2, that's the ratio, and this is 9, that's the ratio between them. There we go, and ratios between them. And therefore we have 1 copper and 6 hydrogen and 2 nitrogen, and oxygen is 9. We can write this formula out as, and that corresponds to copper nitrate 2 dot. So the X is going to be 3H2O. That's what F is. 3 times 2 is 6 hydrogen. 3 times 1 is 1 oxygen there. And 3 times 2 is 6 oxygen. 6 plus 3 is 9. So that's 9. Nitrogen is 1 times 2, because there's 1 here, times 2. That's 2. And copper is 1 here. So that's just 1 copper. And that's it.